Okay, so let's get started. So first things first, let me get to Moodle. So we're in the middle of chapter 11. We still have quite a ways to go. And so we're talking now about probability theory and other interesting topics. So, oh boy. All right. Okay. Let's see. Oh, yeah. So chapter 11, right? Let me just grab this one. And also on Moodle, let's see, let me go back to Moodle. There's several videos here that we still are going to watch. We've already seen so far the math antics, basic probability. I don't think we saw this one yet, though. Did we see this one about arranging a deck of cards? I don't think we did. All right, so we'll see that today. But before we do that, let's remind ourselves where we were. So first, we were talking about probability theory. And before we did that, we sort of took a little detour into the area of counting. We wanted to understand several key principles before we dive into probability theory itself. And so we started out by looking at what are called arrangements. Like, for example, when you have a garage with 3 cars in it, we wanted to know how many different ways there are to park the 3 cars. Now, each way of parking the cars is formally known as an arrangement. Okay, so an arrangement is where you take. Oh, yeah, that's a good question. Yeah, if anyone has a Mac, yeah, this is one of the real problems with going back and forth between Macs and PCs. All right, I'll try to, I'll put them both up there. Unfortunately, what happens sometimes is that the equations and the graphs can get mangled when you open up PowerPoint on a Mac. And you know, the problem is I can't see it on my side. So, all right, I'm glad you reminded me. Yes, if you're having issues with the Mac, I can also give you a copy of these notes in PDF format. And that way we can be guaranteed that you're seeing what I'm seeing. So after we're done, I'll post some notes in PDF. In fact, I'll tell you what I'll do. Let me go back to Moodle right now and put up the PDF version of chapter 11 right now so you can see it during the class. It's quite annoying. You would think that by now they would have figured out a way to make the 2 compatible, but apparently that's just not how things are going to be done. So let's take care of that right now. Here's chapter 11. And this is the PDF version. And so no matter what happens, no matter what computer you're using, you'll have no trouble at all opening it up because it's essentially a picture of what's going on in the slides. Okay, in other words, that's why there won't be a problem because you're actually just seeing a copy of it, not the original. I don't believe you can edit these unless you have the right software, but there it is, so you can actually read it. All right, so that's taken care of. So let's get back to this. So yes, each way we can park the cars is called an arrangement because you're taking all 3 cars and simply changing the order in which you're parking them. And we discovered that there are 6 different ways of doing this. First, by simply writing them out, which always works, but that can take a very long time, especially if you have, oh, it wouldn't let you open them at all. Oh, that surprises me. Usually what happens is you open the slides and some of the equations are not visible because the two systems are not compatible in some ways, and graphs are often a problem as well. So not letting you open the slides at all, that's a different matter altogether. It should let you open them up. I don't know, it might be that it's interpreting those slides as a virus, but this way you should not have a problem. Okay, they should both be completely happy with PDF. All right. Now, and the other thing too is I can't actually write directly onto the PDF. So that's why it's easier for me to do this in PowerPoint, but I can actually, if you want these handwritten notes, I can also save these as PDF and fire them off too. So that way you're not missing anything. Because again, the PDF is really just a photograph of what you're actually seeing here. All right, so each one of these is an arrangement. And I also use the example of posters. If you have 3 posters and you want to hang them up on your wall from left to right, how many different ways can we do this? Well, with 3 posters or 3 cars, it doesn't matter. There's altogether 6 different ways of hanging them. Now, we finally saw the exact reason for this. When you stop and think about it, what's actually happening when you park these cars? Well, first, there's 3 ways of parking the first car. Once that decision has been made, there's 2 cars left for the second car, garage. And then once you've decided which car to put in the second garage, there's only 1 car left for the third garage. So the number of ways of doing this is 3 times 2 times 1, or 6. And that's important because that's exactly how this operator factorial is defined. Here it is. The factorial operator is defined in exactly the way I've just described. 3 is 3 times 2 times 1. So in other words, this follows along exactly with the logic for how many different ways there are to park 3 cars. 3 for the first garage, 2 for the second, and 1 for the third. When you multiply them together, of course, you get 6. So the factorial operator is only defined on non-negative integers. For 0 and 1, they're defined to be equal to 1. After that, then they get a little bit more complicated. For example, 2 factorial is just 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And it just keeps going on. And eventually it gets to the point where they are actually quite large. In fact, if you were to go ahead and go to your calculator and try 10 factorial, you'll see it's already up to 3,628,800. That's a lot. Imagine if you lived in a house big enough where you can hang 10 paintings on your living room wall. That's a pretty big house. How many different ways could you hang these 10 paintings? More than 3 million different ways. That's pretty impressive. 3.6 million ways of hanging those 10 paintings. And let's say you're in a museum, a major museum that has room on the wall for 30 paintings. In principle, those same 30 paintings could be hung in 2.6525 times 10 to the 32nd different ways, which is quite an extraordinary number. So now here I had another example about paintings. This one is a little different. There's only 4 of them. And these are meant to be the actual paintings. It's like this new artist who's all the rage in the city, because this artist puts a colored dot on a white canvas. And so you've got 4 paintings here. Now imagine somebody who's really well off decides to buy these 4 paintings. How many different ways can they be hung on the wall? Well, we already know the answer to that. It's 4 times 3 times 2 times 1, or 24. Or alternatively, we can think of this as 4 factorial. So with 4 objects, there's 24 ways of hanging them. Now, that leads us up to this first video, which, like I said, I thought I might have showed it to you, but now I'm not so sure. Does this ring a bell? Did we see a video about shuffling cards? I know it's in my list, but I thought I only showed you this first one. So I'll tell you what, let's look at it anyway. It's a lot of fun. It helps explain very clearly how arrangements actually work, and it will give you some very surprising results. Okay, so let me just fire this off to you. It's a lot of fun. Take my word for it. You'll like it.
Looking for dinner, maybe?
All right, hold on. So the question in the posed by the video is, how many different ways can you arrange a deck of cards? Sounds like a simple question. Remember, there's 52 cards in the deck. So, well, all right, let's watch it.
Easy. Move over, meal prep, and make way for pre-chopped and pre-portioned.
Pick a card, any card. Actually, just pick up all of them and take a look. This standard 52 card deck has been used for centuries. Every day, thousands just like it are shuffled in casinos all over the world, the order rearranged each time. And yet, every time you pick up a well-shuffled deck like this one, you are almost certainly holding an arrangement of cards that has never before existed in all of history. How can this be? The answer lies in how many different arrangements of 52 cards, or any objects, are possible. Now, 52 may not seem like such a high number, but let's start with an even smaller one. Say we have 4 people trying to sit in 4 numbered chairs. How many ways can they be seated? To start off, any of the 4 people can sit in the first chair. Once this choice is made, only 3 people remain standing. After the second person sits down, only 2 people are left as candidates for the third chair. And after the third person is sat down, the last person standing has no choice but to sit in the fourth chair. If we manually write out all the possible arrangements or permutations, it turns out that there are 24 ways that 4 people can be seated into 4 chairs. But when dealing with larger numbers, this can take quite a while. So let's see if there's a quicker way. Going from the beginning again, you can see that each of the 4 initial choices for the first chair leads to 3 more possible choices for the second chair. And each of those choices leads to 2 more for the third chair. So instead of counting each final scenario individually, we can multiply the number of choices for each chair, 4 times 3 times 2 times 1, to achieve the same result of 24. An interesting pattern emerges. We start with the number of objects we're arranging, 4 in this case, and multiply it by consecutively smaller integers until we reach 1. This is an exciting discovery, so exciting that mathematicians have chosen to symbolize this kind of calculation, known as a factorial, with an exclamation mark. As a general rule, the factorial of any positive integer is calculated as the product of that same integer and all smaller integers down to 1. In our simple example, the number of ways 4 people can be arranged into chairs is written as 4 factorial, which equals 24. So let's go back to our deck. Just as there were 4 factorial ways of arranging 4 people, there are 52 factorial ways of arranging 52 cards. Fortunately, we don't have to calculate this by hand. Just enter the function into a calculator and it will show you that the number of possible arrangements is 8.07 times 10 to the 67th power, or roughly 8 followed by 67 zeros. Just how big is this number? Well, if a new permutation of 52 cards were written out every second, starting 13.8 billion years ago, when the Big Bang is thought to have occurred, the writing would still be continuing today and for millions of years to come. In fact, there are more possible ways to arrange this simple deck of cards than there are atoms on Earth. So the next time it's your turn to shuffle, take a moment to remember that you're holding something that may have never before existed and may never exist again.
Well, that was pretty cool. I think you'll agree. The idea that there's so many different possible ways of shuffling the deck that whenever you shuffle the deck, you might be creating a new arrangement for the first time in the history of the universe. That's pretty interesting to think about. But yes, it shows you just how large these factorials really are, or they can be. So, but I think he explained the whole idea very, very clearly with the chairs and the people sitting in them, how you can count the number of ways of seating any number of people or hanging any number of posters or parking any number of garages. Okay. So anyway, now we're going to see another exciting concept, which sort of follows along logically from this concept of factorial. Okay, so instead of imagining that you have, let's say, 4 paintings and you simply want to arrange them in different ways, what if instead I'm going to choose only some of the paintings to hang on my wall? For example, let's say I have 10 paintings in my collection, but I only have room for 4 of them. That's a very different situation because now there's many more paintings to choose from. And so I would like to know how many different ways I can choose paintings to hang on my wall. So this is now a new area which we will call permutations. Okay, now a permutation is different from an arrangement because we're only picking some of the objects in our collection. But the order in which I choose them has some important significance. And so I'm actually choosing a smaller group from a larger group in such a way that the order in which I select them matters a great deal. And so, for example, let me just throw something up there, a really quick example. What if we, let me throw this example up there. Let's just keep it really simple. Suppose that you own 3 paintings, which we'll call paintings 1, 2, and 3, but only have room for 2 of them on your wall. How many ways can you hang your paintings? All right, so we're going to write them down. 1 followed by 2, 1 followed by 3. Oops. Now, here's the important thing. I now need 2 followed by 1. So here's the thing. Paintings 1 and 2 are different. Let's say painting 1 is a Picasso and painting 2 is a Monet. The order in which I choose the paintings matters because the first one that I pick will go on the left. Remember, I only have wall space for 2 paintings. And so it does matter which one I pick first because if I pick 1 followed by 2, this is what my wall is going to look like. But if I pick 2 followed by 1, this is what my wall is going to look like. And I think you'll agree, these are 2 different arrangements of the same 2 paintings. So I need to make a distinction between 1 followed by 2 and 2 followed by 1. I also need 2 and 3. I also need 3 followed by 1 and 3 followed by 2. And again, if you notice, I'm treating these as different choices, even though they're the same paintings. So in other words, for each choice that I make, there's 2 different ways I could, or orderings in which I could choose them. So each of these choices is known as a permutation because the order in which I select the paintings is important. It determines where they'll be placed on the wall. So there are 6 we can hang the paintings. Six different ways. Each choice is a permutation. It's not an arrangement because we're not using all 3 paintings. It's a permutation because we're only choosing some of the paintings and the order in which I choose them still matters. So there's 6 ways of doing this. Now, you're probably wondering, is there a formula of some kind or a mathematical function that we can use to figure this out directly? And the answer is yes, but we'll get to that in a second. I have another example for you right here that I'd like you to look at. Oh, before I do that, let me save this real fast. Do not want to lose my work, that's for sure. What is today? 4? All right, let's look at another example of this. Suppose that the students of SUNY Purchase decide to start a math club. There are 10 members in the club, and we need to choose a president, a vice president, and a treasurer. Okay, so suppose that the rules of the school require that each club has a president, a vice president, and a treasurer. Now, nobody is volunteering for these jobs. They're like, no, it's okay. Let somebody else do it. So, but we have to have these 3 positions filled. So here's the strategy that we hit on. Every person in the class, in the club rather, is given a number from 1 to 10. We're going to randomly pick 3 numbers by whatever method we choose. We could put slips of paper in a bag or something and reach in and grab them, for example. And then the order in which we choose them will determine not only who gets to be an officer of this club, but whoever gets picked first will be the president. Whoever gets picked second will be the vice president. And whoever gets picked third will be the treasurer. So we pick them. Now, one possible outcome is that we pick student number 3 first, who's now the president, student number 1 second, who's now the vice president, and student number 7, who is now the treasurer. Now, if we had chosen those same 3 numbers, but in a different sequence, for example, 7, 3, 1, while they're the same 3 numbers, now all of a sudden, student 7 is the president, student 3 is the vice president, and student 1 is the treasurer. So these are 2 different choices that we can make when we select 3 students out of 10. So each choice here will be known as a permutation because we're choosing objects from a larger collection, and the order of selection matters, just like with arrangements. So you can think of a permutation as a special type of arrangement where you're not using all the values. I mean, that's essentially what separates the 2. And so the question is, how many different ways can we fill these positions? Now, sitting down and writing this out would take a very long time, and you're bound to make mistakes. So this is where we have to start thinking about introducing a formula. Okay, a formula. So you'll be happy to see that the formula involves the factorial operator. It's a little bit more complicated, but not that much. So the way it works is this. The symbols you're seeing up here, this is shorthand for the number of permutations that can be created by choosing R objects from N. Okay, so in other words, it's assumed here that we're choosing R objects, R's are the number of objects from a larger collection N. So the NPR is the number of permutations. And you can see here's our old friend factorial. It's N factorial over N minus R factorial. So really isn't that much more complicated than what we were doing before. Now, if you have, by the way, I think we discussed this the last time, your calculator, your iPhone does have this factorial operator on it somewhere. If you're not sure, let's go back and look at it for a second. Go to your calculator, flip it over. And then what you're going to do is, let's say you're interested in knowing the value of 10 factorial. Just hit 10. Now the X factorial button is in the extreme bottom left-hand corner. If you hit that button, you'll get 3,628,800. Okay, so I just want to remind you that that is on your keyboard. So therefore, for this question, with the students and the jobs, altogether, there are 10 members of the club, so N is 10, and there are 3 people being chosen for these positions. So R is 3. Okay, so in other words, here it is again. N is 10 because there's 10 members of the club. R is the number of officers that we need to pick. So if you plug these in, you'll see that what you've actually got after doing some algebra is 10 factorial over 7 factorial. So now you can go to your calculator, hit 10, and then hit this button. And I don't think you need the equal sign. Let me just double check that one more time. Sometimes you do and sometimes you don't. It depends on that particular operator. 10 followed by that x factorial. Yeah, no equal sign. You're all set. We'll give you the 3,628,800 for 7. Well, let's try that. Hit 7 followed by the x factorial button, and it will in fact give you 5,040. So you can see altogether, there's 720 different ways to fill these positions. So we're now pretty grateful that we didn't decide to start making up that list, aren't we? How long would that have taken to make up a list of all the possibilities? A long time, let's put it that way. So no, we don't want that, especially when this function is there. Now, if you have a more advanced calculator, many calculators actually have this built into them. Let me just mention that if you're not using the iPhone, take a look at the keyboard on your calculator. For example, the Texas Instruments EA2 Plus, which you might have, has it. It's in the, it's directly above the minus sign. Okay, on the Texas Instruments TI 8384 series, factorial and permutation are found on the math menu under the probability submenu. Okay, they're in there. So just take a look, and that will speed things up even more. If not, well, you know what? Go ahead and use this function. It's not a problem. I think you'll agree this is not a terribly complicated calculation, but it's good to know if it's there, you might as well take advantage of it. Not on this one. The Apple calculator is surprisingly good, but it's not really a scientific calculator. They do what they can. It's got an amazing amount of stuff considering, though. I must say, this is a very good calculator, but man, it doesn't have everything. So I guess they figure for something like this, you can take care of that yourself. All right, now here's another one. Another example, I mean, imagine you go to the track to bet on horses. Now, there are horse racing tracks. New York State has quite a few of them. There's one in Yonkers. And what happens is horses run around the track and people bet on which horse will finish first, second, and third. And the prize money depends on which is which horse is first, second, and third. So you're typically going to be asked to bet on the first 3 places. And so imagine a scenario where there's 8 horses in the race and you're asked to bet on 3 of them. So for example, you could bet that horse number 1 wins, horse number 2 finishes second, and horse number 3 is third. Or you could equivalently, now here's the important detail though, if you bet this 1, 2, 3, this is what has to happen. You won't win if horse number 2 finishes first, for example. But 2, 3, 1 is a different bet, even though they're the same numbers, because in this case, you win if horse number 2 finishes first, Horse number 3 is second, and horse number 3 is third. So if you were asked how many different bets you can potentially place on this race, what you're actually being asked for is how many permutations can be created or are possible when choosing 3 objects from 8. That's essentially what you're being asked. And so N would be 8 in this case, and R would be 3. So here's what I would like you to do, given that we already have seen this formula. Just for the practice, why don't you go ahead and see if you can come up with this number before I show it to you? All right, so you've got your formula, you've got your N, you've got your R. Go ahead and see what you can come up with. It's not a huge number. I mean, it's a fairly large number, but it's not, gigantic. All right, I'll give you a minute and see what you can do. All right, so remember what you're supposed to do after you plug everything in. You're going to have 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. Now, you go to your calculator and calculate them both separately and then plug them in. And so the 8 factorial is 40,320. The 5 factorial is 120. So we end up with 336. So there's 336 ways you can bet on this horse race. Okay, so I think you're getting the idea here. A permutation, like I said, is a selection from a larger group where the order of selection matters. So you're probably right about now asking yourselves, what about a scenario where I'm choosing objects from a group, but the order does not matter? Is that possible? Yes, it is. Let's see. Let me throw in a quick example here. Suppose that you are asked to choose 2 electives from 4 courses for the spring semester. Now, the order, and you'll assume that they all fit in your schedule, of course. How many choices do you have? Well, here's the big question. Hint. Well, all right. Note the order of selection does not matter. Okay, you see why? Because you're just saying, listen, here's a list of 4 electives, pick 2 of them. If you pick whichever one you pick, it doesn't make any difference. It's just the 2 electives. So unlike the horse race where the selection order mattered a great deal, or the students in the math club, Here, it doesn't make any difference which one you pick first and which one you pick second. If you write down that you want to take Calc 3 and physics, let's say, the order is irrelevant. So then how many ways can we do this? Good question. So let's just say that the electives you have to choose from all right, let's say it's calculus 3, physics. I need something that doesn't start with a C. English literature, and I don't know, something with another letter, art history. Okay. So C, P, E, and A, just remember that. C, P, E, and A. Now, how many choices do you have? What choices do you have? Well, the possible choices would therefore be all right, so remember that the letters are C, P, E, and A. You could take calculus and physics, calculus with English, calculus and art history, physics with English literature, physics with art history, and English with art history. Now, here's the thing I want to draw your attention to. If you notice, I don't have P comma C listed as a separate choice because it amounts to the same thing. In other words, calculus and physics are my two electives. The order in which I write those doesn't influence anything. So I don't need to separately include PC, EC, for example, AC. So in other words, I only want the ones where there's two unique choices. So altogether, as you can see, there are 6. Okay, now here's the interesting part. Because the order of selection does not matter, these choices are not permutations. Instead, they are known as combinations. All right, so in other words, when the order of selection does not matter, then we call each choice a combination instead of a permutation. It's an important distinction because sometimes when we choose objects, the order matters and sometimes it doesn't. When it doesn't, they're known as combinations. So, of course, this implies that there's going to be a different formula for figuring out how many combinations we can create. So if with a collection of n objects, if we choose R of them in such a way that the choice does not matter, that means each choice becomes a combination. And the formula for calculating the number of combinations is a little bit messier than it is for the permutations. Not much, just enough, though. We have to pay attention. And so here's another quick example. This is very similar to the one we just did. This time we're trying to paint a house. And we have to pick 2 colors. There's the 4. We have to pick 2. The order in which I choose them doesn't really make any difference. So in other words, if I pick green and blue, that is the same as blue and green. It means the same thing in this context. So how many ways can I do this? How many ways can I choose the colors for my house? Well, again, I'm going to list them. What I've done here in this slide is I've listed the colors that we can choose, and I've listed next to them the choices that actually mean the same thing. So let's say, here's my list. On the left, we have green and white, green and blue, green and yellow, white and blue, white and yellow, blue and yellow. On the right, you'll see that I do not need, let me make a note of this here. These are not separate choices because the order doesn't matter. So in other words, green, white, white, green means the same thing here. Just like green, blue, blue, green. And again, contrast this with the horse race. The horse race, the order makes it really makes a huge difference. Here it does not. So these are all the combinations that we can create when we pick two objects, in this case, two colors from 4. All right, so here's the bottom line. Now, how does this affect the number of ways that we can make this selection? Okay, here we go. I'm going to show you, I've written on the slide here the formula for combinations, but I've also included the formula for permutations so you can see how it's different. All right, and you can see, I'll show you right here, there's only one difference. There's an extra r factorial in the denominator with combinations. And so because of this, the number of combinations is smaller than the number of permutations. All right, just because we have to divide by that extra term in there. All right, so what we're going to do now is figure out how many ways we can paint our house with 4 colors to choose from, and we need 2, using this formula rather than just counting them out. Okay, we'll see how that works. Okay, so remember, there's 4 colors to choose from. N is 4, and R is 2. So when you plug in all these numbers, you're going to see that when you're done here, you've got 4 factorial over 2 factorial times 2 factorial, or since 4 factorial is 24, 2 factorial, you've got 24 divided by 2 times 2, 24 over 4, and just as we found, we have 6 different combinations of colors that can be created when we pick 2 out of 4. All right, well now, you know what? I've got another good example for you. This is a fun example, a very fun example, and one you may have all experienced before. So here's what's going to happen. Suppose you are at the Haagen-Dazs in the White Plains, the Westchester Mall. Today, they are having a sale. Any 2 toppings for $1. Okay, they have 5 toppings to choose from. All right, what could they be? For example, gummy bears, marshmallows, Oreos, or crushed Oreos, whatever. You know, sometimes they're whole, sometimes they're not, but Oreos. What else might they have? How about sprinkles? And let's see, what else might they put on there? Cherries. I don't know. You might put cherries on there. Who knows? All right. Oh, yeah. All right. So I just needed 5 letters. Now, here's the question. Suppose you decide, all right, I have ice cream. I want to get some toppings. And today I want to take advantage of this wonderful sale. So how many different choices do you have? The first question you want to ask yourself is, does the order of selection matter? In other words, suppose that you pick gummy bears and marshmallows. Does it matter if you pick the gummy bears first and then the marshmallows? No. they're just going to dump them all on top anyway. No matter what you say, they're going to just dump them on the top. So the order of selection has no bearing on your ice cream. All right, so therefore, since the answer is no, therefore, each choice is a combination. So now that means what we need to do is go get the combinations formula with the understanding that n is 5. Let me go grab it. Here it is. Well, it's a little early I guess it's a little early in the morning for ice cream, but still, you get the idea. Hold on. N equals 5. R is 2 because we're only getting 2 toppings. All right, here we go. So what I'd like you to do is figure this out for yourselves now that you know. No, you do. If you don't have n factorial in your calculator, there's no shortcut. You literally do have to do all those multiplications. That's right. I didn't notice this until just now. Yes, with the factorial, there is no actual formula. Just multiply them out or use a calculator. All right, so once you try this one and see what you come up with, how many different ways can you choose your toppings? And this knowledge can come in very handy. Suppose you're in White Plains with people and you want to impress them, and you can say, you know, I can tell you right now how many combinations there are. They may not appreciate that, but all right, so take a minute and see what you can come up with. So let me actually get this started with you. Okay, so now it's just a question of plugging in the numbers. Oh, okay. Well, I spoiled the surprise a little. It turns out that there's 10. Now, if you wanted to, you could have written down a list. I made sure that all these choices have different starting letters, so it wouldn't have been that difficult, but let's just say this is easier. And so because the order doesn't matter, that makes these combinations, and you'll use this formula. If the order matters, then you have to use permutations. Okay, so it's always going to be, that's what you're always looking for. Is it the case that the order of selection matters or not? That's how you know. Yeah, if yes, then use permutations like with the horse racing. If no, like with the toppings, then you use combinations. All right, now here's another fun example. How about the game of poker, draw poker? If you played or not played, all you have to know is that the deck of cards, the standard deck, has 52 cards, and you get 5 cards in each player's hand, and the order in which you are dealt your cards does not affect the value of your hand. Okay, it doesn't matter how you pick them up off the table. It doesn't matter what order. What matters is the cards you have. So that means that each hand that we get in it when we're playing draw poker could be considered a combination of 5 cards chosen from 52. So we can ask ourselves the following question. How many different hands can be formed from a standard deck of cards? Well, that's a combination problem where n is 52 and r is 5. Now, with this one, there's a trick that I want to show you because this is going to get very awkward. Let me show you the trick. All right, so if you start this one out, you'll plug in the numbers and say, there's no problem here. But the real issue is that the numbers themselves are going to be very, very large. And so I want to show you an algebraic shortcut for this. So you're going to have 52 factorial, 52 minus 5 factorial. So you actually end up with 52 factorial over 47 factorial and 5 factorial. Now, normally this wouldn't be a problem, but these numbers are so gigantic that, in fact, your calculator will show these first two in scientific notation. So here's what we can do to get around that problem. 52 factorial is equal to 52 times 51 times 50 times 49, as you know. All right, obviously I left out a bunch of them, but 47 factorial equals 47 times 46 times 45, blah, 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 all the way to 2 times 1. So if you notice, this section is itself 47 factorial. So that means I can simplify 52 factorial by writing it as 52 times 51 times 50 times 49 times 48 times 47 factorial. Now, how is that helping me? You're asking yourself, why are we doing this? Well, first, make sure you understand what I just did. Okay, I've rewritten 52 factorial in a slightly simpler way. And the reason for this is so that I can do some cancellation in my ratio. All right, specifically, what I'm doing here is this. Oh, look at that. So I'm left with 52 times 51 times 50 times 49 times 48 all over 5 times 4 times 3 times 2 times 1. Now that's still kind of a nuisance, but compared to dealing with those gigantic numbers, this might be the way to go. So in the numerator, it's still a gigantic number. 311,875,200. So when you finally divide that out by 120, you get 2,598,960 possible poker hands. That's a big number. But here in a case like this, it might be awkward to deal with those gigantic numbers. So in a case like that, you can streamline it a little bit and make it a little bit easier to calculate it. Now, we'll try to avoid gigantic numbers in this chapter. But, you know, let's say you run into one. Here's a strategy for helping you manage the size of these calculations. Pretty interesting, I think you'll agree. All of this stuff is interesting, isn't it? Yes, it is. It's very interesting. Now, I'm going to show you something that you'll find to be very disturbing, because your knowledge of math now is reaching up to levels that many people never get to. It may not seem possible, but already your math knowledge probably puts you in the top at least 30–40% of all people in the country, maybe even more than that. We have to be realistic. A lot of people simply don't know very much about math. So you're kind of creeping up into the higher levels of math knowledge compared to the general population. So here's something that you will probably not have thought about until now. What if you have a locker at school? Now, you may not have one where you are now, but in high school, you may have had one. And what did you have on your locker? A lock. That's why it's called a locker. What kind of lock? All right, remember these guys. In fact, I should probably go look one up, get you a little picture. It's hard to draw these things properly. Oh, I know you've seen these before, unless the technology has advanced so much that I'm way behind in this area. Ah, here we go. The classic lock. Now, if you notice, well, this one has a little key. Well, they don't all have a key, but how do you get this thing open? What do you have to do? You must, at least one of you must have experienced this in your lifetime. First of all, what is this thing called? Okay, well, they've got it listed as a padlock, but most people call it a combination lock. And how do you open it? What do you have to do? Well, there's 3 numbers. So you'll have a combination which consists of 3 numbers. Let's say the numbers are 7, 15, and 22. That means you have to turn to the right 7, to the left 15, and to the right 22. And it pops open and you can get all this stuff out of your locker. Now, let me ask you this question. What if you went into your combination lock and you type, I guess you're not really typing, but you said right 22, left 15, and right 7. Would it open? All right, what do you think? Well, I think you know the answer. It is no. It has to be in the right sequence. Now, there's the thrust of the problem. Okay, watch. Now, be prepared to be disillusioned with, right now, you're going to say, oh my God, how could this have happened? Since the order in which the numbers are entered, each choice is a permutation. Okay, in other words, 7, 15, 22 is one permutation because we're picking 3 out of 35 numbers and the order matters. So here's the question. That being the case, these locks should be called permutation locks instead of combination locks. Am I right? So now when you look at these things, you'll never look at them the same way again. You'll say, oh my God, who came up with this name? They're not combination locks at all. They're permutation locks. Well, maybe we could get a grassroots effort going to formally rename them permutation locks. We can get into the dictionary and change the meaning of this, the name of this lock from combination to permutation. Should we do that? Should we start a grassroots effort to get everybody to rename these permutation locks? Maybe not, but you and I know that these are not named correctly. They are actually technically permutation locks. They're not combination locks. Okay, and now you should be proud of yourself because you know that. Okay. All right, well, now that mystery's been resolved. Why are they called? Well, we don't know why. Somebody picked a name who didn't know the difference. And then the name stuck, but they're not named correctly. Now, here's a fun application of all of this. Talking about order. And we have a video for this too. I'm about to show you a very amusing video. Application. Okay, this is a historical event. Now, in the early 20th century, the famous statistician, Ronald Fisher, was at a party where a woman who was drinking tea complained to the waiter, because they're at a party, they're being, you know, the drinks are being brought to them at the table, that the, I forgot which one it is, but the tea was not poured correctly. She was drinking tea with milk, and she claimed that she could tell if the tea had been poured first or if the milk had been poured first. Now, does that seem plausible? Does anyone here drink tea? Could you really tell the difference? So now here's Ronald Fisher. Now he's one of the greatest statisticians of all time. So I mean, everything he sees and encounters in his life reminds him of some result in statistics. So Ronald Fisher hears this discussion. He says, you know, this might be an interesting opportunity to test one of my ideas. So Ronald Fisher proposed a test to see if the lady could really tell the difference. So this is his idea of an exciting evening. His idea was to have 8 cups of tea, half with the tea poured first and half with the milk poured first. The lady would then taste each one without knowing what had been poured first. In other words, they were going to randomly choose them and give them to her and say, all right, taste each one without knowing what had been poured first. And then write down whether she thought the tea was poured first or the milk. So he's thinking that if she gets a large percentage of them correct, then maybe she does know what she's talking about. So I'm going to tell you more about it after we watch the video. In other words, I'm not going to spoil the surprise. How many did she actually get right? That is in the video. So I want you to see this video, and when we're done, we'll figure out what happened. Okay, but I'm sure you're excited to know what happened. So I'm going to send you this video right now called The Lady Tasting Tea, and we're going to find out what happened. Okay, so first, let's get this over there. Whoever thought that tea could be so exciting? I mean, really. All right, check this out.
Young Latin woman is a good option?
We are in Cambridge, England, 1920. The weather could not have been more perfect for high tea on the terrace. We gathered at the table as a friendly group of colleagues. The gathering had been progressing in a lively fashion, and the teacups were being refreshed when Lady Otterline abruptly stopped the server and pointed out with disdain that he had poured milk first and then tea, rather than abiding by a widely known preference for tea first and then milk. Sidelong glances were exchanged by numerous members of our assembled group as they questioned what difference could it possibly make whether milk or tea were poured first in the cup. It made, according to Lady Otterline, all the difference, a difference she could easily taste. It was at this point that I, as a scientist and amateur detective, decided to step in and proposed a little experiment. Safely away from Lady Otterline's line of vision, 8 cups of tea were prepared. 4 cups with tea poured first, and 4 with milk poured first, always in equal proportions. Happily, Lady Otterline sampled each of the 8 cups and provided the crowd with her judgment of tea or milk first. Remarkably, Lady Otterline identified 8 out of 8 correctly. Could such a feat be accomplished by sheer guesswork? Now, as I mentioned, I'm a scientist above all. As such, I left this little party with more than just some favors. Indeed, I took with me much food for thought. Try my experiment yourself. Consider all the possible results. In what order should your cups be presented? How many cups must be correctly identified to conclude that your subject can truly tell the difference? You will undoubtedly come away with a greater understanding of inferential statistics.
Hmm. Oh no, it looks like the Zoom crapped out on us. Can everyone still hear me? Oh boy. All right, well, once again, I guess we're gonna have to reboot my computer. So I'll be right back with you in a minute.